Welcome to the first session of Network Analysis 1. You're watching GATE series, Electronics and Communication Engineering. We'll begin with Kirchhoff's circuit law. Kirchhoff's circuit laws consist of Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law is basically based on conservation of charge and energy. It states algebraic sum of all voltages around any closed loop of a network is zero at all instants of time. So if we have a closed loop in a given network, and if we sum all the branch voltages of that closed loop, the total voltage is always zero. That is Kirchhoff's voltage law. We'll move on with Kirchhoff's current law. Kirchhoff's current law states at any node, the sum of currents flowing into that node is equal to the sum of the currents flowing out of that node. Simply to place, the current entering a node in a circuit is equal to sum of all currents leaving that node. Or simply to say, at the node, the total current is zero. Sum of all total current is zero. Series and series parallel network. If R1, R2, R3, R4 and so on up till Rn are n resistors connected in series, that is, they are connected end to end, then the total resistance is simply the sum of the values of all those resistances. Moving on, resistances in parallel. If R1, R2, R3, R4, so on up till Rn are n resistances connected in parallel, that is across each other, then the equivalent resistance R equal is given by the expression R equivalent is equal to the equivalent resistances of all resistors in parallel, or to simply to say 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on up till 1 by Rn. Series parallel and series parallel network going to capacitors. If C1, C2, C3, so on up till Cn are the different capacitances connected in series, then the equivalent capacitance C equivalent is given by the expression 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on up till 1 by Cn. Similarly, capacitances in parallel, if they are connected across each other, then C equivalent, which is the equivalent capacitance of all capacitors, is given by the expression C1 plus C2 plus so on up till Cn. Moving to the next slide, consisting of inductors. If inductors having inductance L1, L2, L3, L4 up till Ln are connected end to end, then the total inductance of all those inductors in series is given by L equivalent is equal to L1 plus L2 plus so on up till Ln. Similarly, for inductors connected parallel to each other, that is across each other, the total inductance L equivalent is the equivalent inductance of all those inductors. 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus so on up till 1 by Ln. Moving to the next topic, source and network transformation. So we will begin with source transformation. So here you can see a voltage source and a series resistance connected in series with the voltage source. So we begin with this circuit, and adjacent to this circuit there is one more circuit consisting of current I and a parallel resistance R. So what is the relationship between these two circuits? It is given by the source transformation. Source transformation says a voltage source V with its internal resistance R, so this is the internal resistance R, can be converted into an equivalent current source I. So this is the equivalent current source I placed in parallel with the resistance R. So this is a parallel resistance, and the value of I is given by V by R. So this value of the current in the current source is given by the ratio of V, that is the voltage, divided by resistance R. Similarly, adjacent to this circuit, there is one more circuit with current source I and parallel resistance R, and another circuit with voltage V and R resistance in series with V is located at the rightmost end. Source transformation relates these two circuits by the source transformation law. The source transformation law says a current source I in parallel with its internal resistance R. So I with internal resistance R can be replaced with voltage source, V is a voltage source, in series with R, where the value of V is given by V is equal to I into R. V is equal to I into R. Next, moving to the network transformation. Ideally, we are having two types of network. One is the pi network and another one is a T network. So this is a T network. It is of T shape. Pi network will be discussed in the next slide. So pi network consists of impedances connected in pi form, whereas T network shows impedances connected in T form. Okay. If Z1, Z2 and Z3 are the three impedances connected in T form, then what is the pi transformation of this T network? This is a T network. So what is the pi transformation? How do you convert the T network into pi network? So pi network impedance ZA is given by the product of Z1, Z2, product of Z2, Z3 and product of Z1, Z3 divided by Z2. So if we have ZA here, So ZA is common to Z1 and Z3. So other resistance impedance Z2 will be at the denominator. So ZA is across 1, 1. So Z2 will be the other impedance which is not in common with Z1 and Z2. So Z1, Z2, Z2, Z3, Z3, Z1 divided by Z2, which is the other impedance which is not in common with ZA. Similarly, ZB, which is the impedance across this network 1 and 2. ZB is across 1 and 2. So Z1, Z2 plus Z2, Z3 plus Z3, Z1 divided by Z3. Z3 is not common to 1, 2. It is away from 1, 2. This is away from impedance 1, 2. So ZB is connected across 1, 2. It is an impedance which is equivalent to the impedance across 1 and 2. So 1, 1 dash you have ZA, 1, 2 you have ZB. And finally 2, 2 dash you have Z1, Z2 plus Z2, Z3 plus Z3, Z1 divided by Z1, which is not common to 2, 2 dash. So this is T to pi transformation. We have another transformation pi to T, which we will see in the next slide. Pi to T transformation. The impedances Z1, Z2 and Z3 of a T network are expressed in terms of impedances of a pi network ZA, ZB and ZC. So here you can see ZA, ZB, ZC are impedances of the pi network. This is in pi form. Okay. So how to find Z1? So Z1 is the first impedance in the T network. So it will come across 1 and ZB. So ZA, ZB. So it will be here. Z1 will be here. So Z1 is equal to ZA, ZB divided by ZA plus ZB plus ZC. So Z1 will be ZA, ZB, which is common to 1 divided by ZA plus ZB plus ZC. Z2 is ZB, ZC by ZA plus ZB plus ZC. Z2 is ZA plus ZB, ZC by ZA plus ZB plus ZC. So where is Z2? Z2 will be across 1 and 2. 1 and 2. So it will be across this. So one you have here, another you have here, and third one will be here. So this T network it will be. So this will be T network. So this will be common to ZA and ZC. This will be common to ZA, ZB, and ZB, ZC, you have one common. So you have T network out of this pi network.